All right, so I think there's two questions here. Um, it tells me that the door is closed in 1 second, and that it makes let's see, perpendicular to the wall. So it makes a 90-degree turn in 1 second. So I think if we started at Newton's second law for torque, which I think is a reasonable place to start, um, we would have to know what the acceleration of the door is in order to use this formula. They're asking us to figure out if the box applies a constant force perpendicular to the door, and if it is mounted 33 centimeters from the pivot, door is wide. Actually, I don't know why this extra information is here unless we were asked to figure out the force on the door. We can get from this. No, I'm sorry. We can get from the mass here and this measurement, we can get the moment of inertia of the door, and we have enough information to get the acceleration of the door. So this might be extra information, but if we wanted to find the force on the door, we could use that. But they're asking for the torque on the door, so let's see if we can kind of work that out. To get the acceleration, delta theta, omega naught, omega, alpha, and t. We've got one here, unknown, starts from rest. We'll need this in radians. So what's 90 degrees in radians? Okay. That's still common stuff, so there we go. I would probably use delta theta equals 1/2 alpha t squared plus omega naught times t to figure out what alpha is. So that's going to give us pi over 2 equals 1/2 alpha times 1 squared. So it looks like alpha is going to be 3.14 radians per second squared. Now for the moment of inertia of the door, I'm going to treat it like a bar about an end. So that's going to be 1/3 ml squared. So we have the mass of the door and we have the width of the door. So 80 kilograms and is it 80 centimeters too? 80 kilograms and 80 centimeters. All right. So numbers. So I get, that can't be right. 80 squared times 80. Oh, it's 0.8. Sorry. My God, that's huge. That's a big door. So 0.8 there. That'll be better. 80 centimeters. So that's a little more reasonable. So like that number just too big. So 0.8 squared times 80 divided by 3, and I get 17 kilogram meter squared. All right, so just put these together. Net torque equals I times alpha. This must be the unbalanced torque acting on the door. So looks like 54 meter newtons. If this were a test, I wouldn't leave that here. I'd ask for the force too. And we can get that pretty easy because they tell us where the force is applied to the door. So if we take that and assume that the only torque acting on it is the evil box, then R times F times the sine of the angle has to equal that 54 meter newtons. They tell us that it's pulling perpendicular to the door, so that's a sine of 90. We don't know what the force is, but they tell us that it pulls at a point that is 33 centimeters from the pivot. You can use that to figure out the size of the force. So, and I do want to go that step because divide this by 0.33 and get that the force is 162 newtons. Kind of putting that into a little bit of perspective, That's pulling with about 30 to 40 pounds of force. So it's not huge, but you got to be careful when you work on those things because they can snap back and get you. It's not going to be pleasant. So that's it. There's also all sorts of adjusters up there to try and make sure the door closes but doesn't slam. It's not working right now because the door's slamming, but it's supposed to. There's like 3 adjusters for how hard it pulls on it, when does it relax that force as it gets closer to the jamb, and actually the ability to pause the door as it gets close enough to the jamb so it doesn't slam too hard. It's a delicate balance, making sure it closes and latches but doesn't break the door jamb. But there you go. A bicycle wheel is a ring of radius 40 centimeters and 1 kilogram. If the spokes add negligible inertia, what force is required to get the wheel spinning at 1,800 rotations per second if the chain of the bicycle is acting on the sprocket that has a radius of 4 centimeters? All right, so the information presented here appears to be information I can use to figure out the moment of inertia of the wheel. We're to assume that the moment of inertia of the wheel is a ring, so that's mr squared. And we have the radius and the mass, so 1 kilogram and the radius 0.4 squared. So that's 0.16 kilograms meters squared. So that's our moment of inertia. We want to get the wheel spinning 1,800 RPS. So that's a angular speed, so 1,800 rotations per second. In order to do this, my alpha for Newton's law has got to be in radians, so I have to convert that to radians before I can use it. So 1,800 times 2 pi. So that's a lot, 11,304 radians per second. Well, they don't tell us how long it's going to take to get to that speed, so pick a time. How long do you want to take to get to that speed?
10 seconds.
Okay. So we'll say 10 seconds, assuming starting from rest. All right, so just divide that by 10, and we'll get our acceleration. So 1,130 radians per second. And now the net torque will be equal to 0.16 times 1130, and that's 181 meter newtons. So the force is being applied 4 centimeters from the pivot point, so 0.04 times F times the sine of 90. Because it's a sprocket, it's going to act like a pulley, so the force is being applied perpendicular to the radius, and that's going to have to equal 181. So big step up in force there, 4,522 newtons. That's probably a little unrealistic, but it's okay. But yeah, without the time, you couldn't really do something. You need time, but I mean, something reasonable, 10 seconds to get up to speed, that's not unreasonable. So number 8, I mean, this is the solution as we did it with a 10-second time interval, but they tell us the bicycle wheel is a ring of radius 40 centimeters and mass of 1 kilogram. If the spokes add negligible inertia, what force is required to get the wheel spinning at 1,800 RPS if the chain of the bicycle is acting on a sprocket that has a radius of 4 centimeters? So without a time, you have an initial velocity and a final velocity, but you have no other variables, so you need something. So she just suggested that we use 10 seconds as our time. So that's perfectly fine. So we did 10 seconds and used that to figure out alpha. We just used the motion equation for it, assumed that it was a straightforward uniform acceleration. Does that make sense? So then after that, moment of inertia, mr squared. Net torque equals I alpha. So we use the moment of inertia that we calculated from the prior part, and we use the acceleration to figure out what the net torque was at 181 meter newtons. And then we just set the single torque acting on the wheel. That's not exactly true. There'd be multiple torques if it was actually on the road, but they're not asking about that. So we talked about a single torque acting on the wheel, what it would take to get it to just spin up to that speed. So this would be you with your bicycle like upside down, spinning the pedals like you did probably when you were a kid. Same idea here. So we did a torque arm length of 4 centimeters and how much force would be required to get to spin up to that speed in our 10 seconds, and a way excessive amount of force there. But lucky for you, if you're using a bicycle, you probably have several torque arms in place. You know, you don't spin the wheel directly, you spin it by spinning the pedals, and there's lots of leverage in there. So, but that's all the problem is. Yeah? Well, let me make sure everything's good about this one. Are we good with that? Yes. All right. So number 6. A potter's wheel, a thick stone disc of radius 0.56 meters and mass 100 kilograms, is freely rotating at 50 revolutions per minute. The potter can stop the wheel in 6 seconds by pressing a wet rag against the rim and exerting a radially inward force of 70 newtons. Find the effective coefficient of kinetic friction between the wheel and the rag. All right. There's a lot of data there, but let's get an idea of what we're talking about here. I think we're going to assume the potter's wheel is a disc, and it is spinning. They give us the RPM, and we're going to apply a force to the disc. They said radially, so we're pushing this way. This is going to be a normal force. So this is the normal force acting on the edge of the disc. So if there's going to be friction, and they kind of assume that there is, the frictional force is going to act this way due to the presence of our normal force acting on the disc. Does that make sense to everybody? All right. Net torque equals I alpha. And in this case, the torque is going to be negative. It's going to be from friction. Actually, I should write this different. So I'll write negative torque due to friction equals 1/2 mr squared times alpha. And I think we can, I don't know how much you're going to need to prove this, but I think friction is going to be mu times the normal force. And therefore, if I sub that in, I'll get minus R times mu times the normal force. I think it's pretty clear that it's going to act perpendicular to the torque arm, so I'm just ignore the sign of 90 degrees. And that equals 1/2 mr squared times alpha. We don't have alpha, but we have information we could use to get alpha. They tell us it takes 6 seconds for the wheel to come to rest from its initial speed of, I don't remember even what that is, 50 revolutions per minute in 6 seconds. So I think we can come up with alpha with that information. Omega is 50 RPM. That's initial. Final is going to be 0. And they tell us the time is 6 seconds, so we just need alpha from that. I will have to convert that RPM into radians per second, though, before we go any further, so let's do that part. We'll get rid of the rotations by multiplying by 2 pi. That'll give us radians. And then, let's see, we'll get rid of the minutes by converting to seconds. So, I don't know, 6.28 times 50 divided by 60. I get 5.2 radians per second. Anybody good with that? So alpha is going to be 0.87, well, it's negative 0.87 radians per second squared. Any questions about that? Alrighty. So back over here, I can cancel one of the r's, but not both. We're looking for mu, so I'll have negative mu equals mr alpha over 2 times the normal force. I believe it was a 100 kilogram wheel with a radius of 0.54 meters and an alpha of negative 0.87, all divided by 2 times, and I don't remember what the normal force was, but they told me, I believe, 70 newtons. Okay. So 2 times 70. Negatives cancel out. Coefficient of friction should be a unitless value. It shouldn't be positive. I mean, it's not going to be negative. So that's it. I can't think of anything else more to do here. Does that answer your question? All right. I'd say kind of a level 1-ish, maybe 2 kind of problem. I think this would be a reasonable multiple choice question. I don't think it's a reasonable FRQ. It could be part of an FRQ, but it would not be the entire question, if you take my meaning. The question involves finding the moment of inertia of a water molecule. So let's see, our oxygen, and we'll have a couple of hydrogens out here. So hydrogen, all right, so I'm going to try and make this look as reasonable as possible. Okay, so there's our water molecule. And I'm going to draw a red line through the middle here. And the reason I want this in here, I think it'll make sense, but maybe not, I don't know. The water molecule has symmetry to it. So I know that the center of mass is going to lie along this line because of the symmetry that's there. So I can treat this as 2 point masses. One that's at the center of the water molecule and another one that's over here where these two would line up along the x-axis, because we just want to find the center of mass first. So I'm going to use the center of mass formula for a one-dimensional center of mass, which is mx divided by the sum of m. Any question where I got any of those from? All right. For the time being, we don't know this length. We can calculate it if we'd like. But let's just say that this length is d for a minute. Because I'm going to, not because I'm trying to like obfuscate things, but this length is 95.7 picometers. So we'll get to how to use that to figure out where this is in a minute. I think you'll understand why we could just do this symbolically real quick. So the center of mass, remember, is a location. So we're looking for a place. The first mass is the oxygen at 16, but it's located at what I'm going to call the origin. And the hydrogens have a mass of 2, and they're located at D. So if I wanted to figure out what the what percentage of the way from A to where from the oxygen to where the hydrogens are located, it would be whatever this ratio is, and that's going to be 1/9 D. So we're talking about a pretty small distance anyways, with the center of mass being maybe here. Does that make sense? So that's how you'd find it. Now, if you want to figure out where that actually is, you'll have to put in the angle, half of the angle here, and use your 95.7 picometers to figure out exactly how big D is, using probably cosine. And then from there, you could figure out where the center of mass is by just multiplying the 1/9 times that, and I'll tell you where the center of mass is. Now, I don't want to use that to find the moment of inertia, and that's because, remember, if this is our pivot point, then I have to figure out this distance and this distance. They'll be the same, but they're going to be really close to 95.7 picometers. The only difference is that there's this little tiny distance here, and the water molecule is also going to be oscillating back and forth along that. But it's such a small distance compared to the other two that it's really not going to contribute very much to a moment of inertia. So I'm going to just assume, and the problem asks whether we can or not. I'm doing it because I'm lazy. I just don't feel like finding out that distance. But if you want to do all that triangle math, then go ahead. But the whole point is for you guys to understand how moment of inertia works. If we are shaking the water molecule from here, we want to find its moment of inertia, then it is the sum of mr squared from I equals 1 to 3. There's 3 objects, the oxygen and 2 hydrogens. But I'm going to say it again. We're doing it from the center of mass of the oxygen. So our first object is the oxygen molecule. I'll do 16 times 0 squared. And then I have 2 hydrogen atoms that are the same distance away from the oxygen atom. So they contribute the same amount to the moment of inertia. They have a mass of 1, and they are 95.7 pico, which is times 10 to the negative 12 meters. Now, the truth is, they don't have a mass of 1. They have a mass of 1 proton. And a proton is 1.67 times 10 to the negative 27th kilograms, I believe. Somebody probably should check my math on that, because I'm not sure I have the right value. But it's on your equation sheet. You have the mass of the electron and mass of the proton. I'm sure it's given. So you would not be expected to memorize it, but it's just one of those numbers I think I have. So this would actually give you the moment of inertia of the system. So is it on there? It's on the first page with all the other constants towards the top. No? All right. Yeah, electron's 9.11 times 10 negative 31, so I don't use this mass very often, so it doesn't come up much. But this is our answer. I'm sorry, this is squared. So if we actually want to work it all out, 2 times 1.67 times 10 to the negative 27th times the 95.7 times 10 to the negative 12 picometers, but that has to be squared, giving me a moment of inertia of 3.1 kilograms meters squared. Oh, wait. 3.1 times 10 to the negative 47th kilograms meters squared. Moment of inertia of a water atom. It's actually a little bit greater than that, because although the center of mass is here and this distance is a little smaller, that distance exists, and that's 16 times the mass of a single proton, but it doesn't change it very much. We're talking just a shade of that tenth. But so for all of you struggling, I hear your struggles, but I'm not going to be particularly empathetic, not because I'm not an empathetic person, but because this is what you're up against. And I don't think you might have looked at the homework seriously enough about what it is you're going to be expected to do. There are 3 forces acting on the wheel, right? So I assume you started with something like weight acting downwards, mg. Normal force acting upwards, but it acts at the point of contact, and friction acting this way. So friction there. I'm going to make, I think, a couple of decisions here that I'm going to need for the rest of this problem, and that is that this is the positive direction. And the wheel starts with a velocity of v naught, a linear velocity of v naught, but also starts with a initial angular velocity of 0. It's not rolling yet. It's going to begin rolling once there's an unbalanced torque to cause it. They tell us to start with Newton's second law and derive a differential equation. And they say exactly what they want us to do. So what force is acting on the wheel. It's the only unbalanced force. So, and it's in the negative direction. So negative friction equals m dv dt. I mean, making a differential equation is just a single substitution. And you're not going to really catch sympathy if you can't come up with the relationship for friction. Mu mg, it's on level ground. So now do the same thing for net torque. I'll give you a minute, then I'll pick one of you. That'll be fun for me. This is all that's necessary for part one. It says, using Newton's second law, derive a differential equation that relates the velocity of the wheel to time. That's what this is. Yep. Which one? I don't believe so. I believe that this torque is going to cause the wheel to increase its rotational speed. Would you agree? Yeah, it's going to cause it to spin in this direction. So I think we move on to the next part. This again, I understand you guys saying, I don't know where to begin. This is hard. Yeah, it's hard, but it's not impossible. They are very clear about what they wanted you to do. I think this is why students didn't do well in this problem, is because they just didn't follow the directions. They are very clear about the directions. And what they ask you to do next, they are very clear about. Derive an expression for the magnitude of the following. The linear velocity of the ring is a function of time. You have a differential equation right now. They're asking you to come up with the function. Now, don't hate me for this, but you don't have to do it the way they're suggesting. But if you look closely, I have mu g equals dv dt. And whether you know what this means or not, the left side of this is a constant. And the right side is acceleration. This is an object with a constant acceleration. You can use a motion equation. I'm not going to, because we know more things, but you could just straight pick a motion equation. But you'd have to pick the right one. And only two of the Galilean motion equations are technically motion equations. They're the first two. V equals at plus v naught. That is a true motion equation. And delta x equals 1/2 at squared plus v naught times t. Those are the two actual motion equations. They tell you a future event when given initial conditions. That's why they are the only two that are true motion equations, and they are what you get when you take the antiderivative here, something we did talk about. So let's go over here and talk about doing that. We have minus mu g equals dv dt, which is actually acceleration. If you remember September, but I know asking you guys to remember things is tough, but in September you found the antiderivative in order to find the other motion equation. So what is the antiderivative of negative mu g with respect to t? Well, negative mu gt plus a constant. The constant represents the initial velocity of the object, which we were told was v naught. This is v as a function of t. Straight out of what we did first semester. The other one? Sorry, this one's not negative, this is positive. Take the antiderivative with respect to t. This is also a constant. Put in your boundary condition, the initial velocity. There. I have omega as a function of t, I have v as a function of t. These were very prescriptive. You have a procedure to do these. You didn't use it, but you should have. Draw a free body diagram. Break it up into components. Net force equals ma. I mean, it was very straightforward. It's where you go from here, I think, that's actually hard. But if you couldn't get here, you're not going to be able to do the rest of the problem. Because the rest of the problem asks you, how long does it take until the system is rolling? They want a time. And if you don't know what that means, you have no idea where to go from here. But if you look closely, this velocity is becoming a smaller and smaller number. Right? At t equals 0, it equals v naught. And for every time after that, the velocity is becoming a smaller and smaller number until it stops, right? Because this term is getting bigger, and that term is negative. But the angular speed starts at 0 and becomes a bigger and bigger number. So the angular speed is increasing while the linear speed is decreasing. Does that make sense to you guys? Well, we know that this is rolling. This is when rolling takes over, and we're no longer sliding. When that happens, but the function for v is becoming a smaller number, and the function for omega is becoming a bigger number, they're eventually going to be equal. Find out when. Plug it in. Solve for t. That'll tell you when it happens. I'll leave it to you to figure out where it happens. But that's what those 3 questions are at the end of this. When is it rolling? And then where is it rolling? This is a tough question. But they are pretty clear about where they want you to start.